So some of our key features, as you see as we go through this, you've been talking about these ones for a long time. Some of them are still a little bit newer, so we'll be going over those. So over here we have just the graph of a function drawn for us. As you notice, there aren't any arrows, so these have a distinct start and stop point to it. It doesn't keep going on forever. So we're going to answer our questions based off of that graph. So first one, state the y-intercept of the function. Let's go over to the function, find where it hits your y-axis. It hits it at 2. So our y-intercept is 2. That one, as I said, that's one of the ones you've been doing a long time. B, state the x-intercept of the function. What is the alternative name that we give the x-intercept? So before we actually find them, does anybody remember what else we call the x-intercept? It's got 2 other names. Yep. Roots is one of them. Anybody remember the other name? Begins with a Z. Zeros. Roots, zeros, x-intercepts all mean the same thing. And that's just where you hit your x-axis. So in this case, we actually have 2 x-intercepts. So we got to add 1, 2, 3, 4, 5. Negative 6. And the other one is at 1, 2, 3, 4. Positive 4. So x equals negative 6, x equals 4. So then C, over the interval of negative 1 is less than x is less than 2, is f of x increasing or decreasing? So we're going from negative 1 to positive 2 on our graph. So I'm going to go to where x is negative 1. Here's where my graph is. Here's where x is 2. So if I connect those two, what is our graph doing? It's increasing because it's going up. So our graph is increasing. D, give the interval over which f of x is greater than 0. So you're looking for when the function is greater than 0. Numbers that are greater than 0 mean that they are positive, so we're looking for positive values here. What is a quick way of seeing this visually? So if our graph is positive, our quick way of seeing this visually is it's above the x-axis. So whenever that graph is above your x-axis, that is when it is positive. So if we take a look, basically from this root, here it's positive, 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 all the way until our other root. So once it hits that x-axis, that's when it switches and becomes negative again. So then it's from negative 6 to positive 4 are 2 roots that we found up in part B. So you could write it like that. That is our interval notation. You could write it in inequality, which would be negative 6 less than x less than positive 4. Either of the 2 notations work. I find people generally prefer the interval because I think it's easier. So parentheses negative 6 to 4. All right, next one. State all the x coordinates. So we're not writing a full point, we're just looking for those x values. So just write the x coordinates of the relative maximums and the relative minimums. Label each. All right, so I'm going to make a little list. Max and mins. So relative maximum, what it means is just in that point in time, it looks like a maximum value, but it's not the absolute highest that it's going to be. So like, for example, this point right here is what we call an absolute max, because that is the highest that that graph is going to get. Nothing is ever going to be higher than that point. So just like this point over here is what we call our absolute min. So that's our absolute lowest it's going to get. There will be nothing lower than that. So we have what we call 2 relative maximums. So again, it's kind of a high value for that area of the graph, but it's not the absolute highest. Right here is a relative max. I just shortened it down to just R max. So that's a relative max. It's kind of a maximum, not the highest. Right here is our other relative max. So again, it's a little higher than the other parts, but it's not the absolute highest. So let's find those x values. So this is at 1, 2, 3, 4, so negative 4. And then we'll find the x value for our other relative max. It's at 1, 2, 3, 4, 5, 6. So our two relative maxes are where x is negative 4, where x is 6. So now we got to find our minimums. So right here, that's a relative min. So again, that's a low point at that area, not the absolute lowest, so that's when x is a 1. And then here is our other relative min. The low point, not the absolute lowest though. So that's going to be when x is a 1, 2, 3, 4, 5. So 1 and 5 are where our relative mins are. F, what are the absolute maximum and minimum values of the function? Where do they occur? So max, min again. So we've already picked out what our absolute max and our absolute mins are. So our absolute maximum value, so the highest it goes is 1, 2, 3, 4, 5, 6, 7, 8. When they ask for the maximum value, all they want is that y value of how high does it actually go. The part of where do they occur, that's when they want the x portion of it. So my absolute max happens when x is a 2. It occurs when x is a 2. So the maximum value is 8. It happens when x is a 2. So now let's do our absolute min. So our absolute minimum value is 1, 2, 3, negative 4. And it happens when x is 5, 6, 7. Yep, negative 8. So again, when they ask for the max or min value, they just want y. Where does it occur? That is your x. State the domain and range of f of x using interval notation. So domain, those would be our x's. So we've already figured out my furthest most left x value. That is a negative 8. So then over here we go all the way to 1, 2, 3, 4, 5, 6. So our domain goes from negative 8 to 6. Now, are there open or closed circles at negative 8 and 6? Closed. You would see a very distinct open circle if they wanted it to be open. Since it doesn't really look like there's a point there, that means those are closed. So in our interval notation, those would be brackets. So our domain goes from negative 8 to 6 with brackets because negative 8 and 6 are included. For our range, I don't even really need to flip back up to the graph because I've got my absolute max and my absolute min values right here. That's going to be your range, your absolute minimum and your absolute maximum. So my range goes from negative 4 all the way up to positive 8. Again, there were absolutely no open circles on our graphs, so brackets, because all those values are going to be included. All right, then our last one, h. If a second function g of x is defined by this formula here, then what is the y-intercept of g? So, can't really tell just yet. You're going to want to distribute that 1/2. because then we'll be able to figure out what our y-intercept is. So if I distribute 1/2, I get the 1/2 x plus 1/2 times 2 gives me a 1. Now this is our linear function that we're used to seeing, our mx plus b. So what is our y-intercept based on that equation? 1. Your b value. Linear is always that last number, so our y-intercept is a 1. So right here, all I've already typed out for you are a whole bunch of vocab words for you to be able to study, because you need to know what these are. Y-intercept, x-intercept, all that good stuff. Increasing, decreasing, constant, positive, negative, zeros, absolute maximums, relative maximums, minimums. All right. So then we have 4 new ones that we're going to be talking about today. Now when we talk about a continuous graph, what that means is it's all connected and flows as you go from the left to the right. So for example, if you draw a picture of a line, that is a continuous graph because you can draw your line all in one pencil mark. It's continuous, it goes on. A parabola would be a continuous graph. You could draw that curve all in one little pencil stroke there. Discontinuous simply means your graph has different jumps to it and it's not all connected. So discontinuous, we've dealt with it a little bit in algebra. Like for example, piecewise functions, which takes different pieces of graphs. So like if you have like a linear piece here and then like a curve over there. This graph would be discontinuous because the 2 pieces aren't connected together. You've got this little section over here and then you got a little jump over to that section over there. So that would be a discontinuous graph, not all connected. Even functions are symmetric over the y-axis. And then your odd functions are symmetric through the origin. And we're going to play around with figuring out even and odd functions. All right, so let's take a look at some examples. So symmetry, the fact that it's an even function, so it's symmetric over the y, and the fact that it's an odd function, so it's symmetric through the origin, that can help you figure out sketches of graphs if you need to do them. So if you have half the point and you know it's symmetric, you can just draw your other half based on whatever it's symmetric over. If an equation is symmetric with the x-axis, then remember it's not actually a function, because it would look something kind of like this. So it would fail the vertical line test, not actually a function. So if it's symmetric over the x-axis, not a function. So even odd test, again, even functions, you can replace x with negative x, and you get the same exact y values. It wouldn't change anything. That's how you know it's going to be an even function. Odd, if you replace x with negative x, then you get the negation of the y value, so you get the opposite. So if you had a positive 3 and you end up getting a negative 3, that's the negation of it. So even and odd, easiest to test and notice by actually looking at the graph of it. So if we look at number 1 here, is this symmetric over the y-axis? Yeah. If I fold that paper up on my y-axis, it's going to be exactly the same. So this is what we call an even function. It is symmetric over that y-axis. So let's look at number 2. Is that symmetric over my y-axis? No. Is that going to be symmetric through the origin? No. So this is neither. It's not even, it's not odd. It's just a function. So then 3, again, is that symmetric over the y-axis? No. Would that be symmetric through the origin, though? Yeah. Through the origin is the one where I kind of like picture in my head, if I flip it under 180 degrees, it would look exactly the same. So that one is odd. Symmetric through the origin is odd. When you have a table of values, it's a little more difficult to see, but it is possible. So again, you want to look at, for example, 1 and negative 1. It's the same numbers, just one's positive version, one's the negative version. So if I plug in a negative 1, I get a positive 3. But if I plug in a positive 1, I get a negative 3. It's not even, because I would have gotten the same exact number if I had done that. That would tell me it was even. Potential to be odd, because they switch. This one gives you positive, this one gives you negative. So we want to check the next ones. So if I look at negative 2 and positive 2, that doesn't help me much, because 0, you can't change its value. 0 is 0. It's neither positive nor negative. So then I'm going to look at my 3's. So negative 3 gives me negative 15, but positive 3 gives me the opposite of positive 15. So this is going to be an odd function, because the negative versions and the positive versions give you the opposites. One stays negative, one turns positive. Let's write in there an example of an even table, just so you can see what it would look like. I'm going to call it g of x. All right, so negative 3, negative 2, negative 1, 0, 1, 2, 3. So for an even table, what will end up happening? I mean, this one I'm going to have a vertex of 0, 0. But both my negative 1 and my positive 1 would give me the same number. They would both give me, for example, positive 1. My negative 2 and my positive 2 would give me the same number. My negative 3 and my positive 3 would give me the same number. That's an example of what an even table would look like. So whether you plug in the positive version of a number or the negative version of that number, you get the same answer. That's an even. Odd gives you the opposite sign-wise. So then looking at our little mapping diagram, to be quite honest, even as a mapping diagram, it makes absolutely no sense to me. I like to make this a table. So then let's see here. Negative 3, negative 1, 1, 3, and 5. I like to go in order from least to greatest in my x's. So let's see here. Negative 3 goes to positive 8. Negative 1 goes to 4. Positive 1 also goes to 4. Positive 3 goes to positive 8. And 5 goes to 6. There we go. So I got my table. The table's a lot easier to see. So really, the 5 doesn't help me out much as far as figuring out whether it's even or odd, because there is no negative 5 in my diagram. So that's not helpful. So if I look at my 1s, my positive 1 and my negative 1, they give me the same exact answer. So this looks like it's going to be even. Negative 3 and positive 3 also give me the same exact answer. So this tells us this is an even function. Your negative version and your positive version give you the same answer. It's even.